Hi everyone. In this video, I'm going to electrically restore this radio receiver that used to fly around in a Boeing B-17 in World War II. Very neat receiver. And then, once this is electrically restored, at the end of the video, we'll take a listen to it and see how well it performs. Should be a lot of fun. I previously, in a previous video, built this power supply for this radio receiver here and showed the entire process of that as well. So this is this exact box that this is right here, and it started out just like this. I took the wrap off it, and this is how it ended up right here, right down to the wrinkle coat finish. So if you're interested in seeing how this power supply got built, you can check that out. It's in my videos list as well. So that was a lot of fun. So the reason that I built this external power supply for this radio receiver here is way back when these things were on the planes have a 24-volt supply on them. And this thing had a thing called a dynamotor inside, and that dynamotor sat right in here on the upper side of the chassis. That dynamotor makes a lot of noise because basically it's the old version of a modern inverter. So you know how you go out and you say buy an inverter for your car that plugs into the lighter socket, it takes 12 volts and say steps it up to 120 so you can run appliances in your vehicle, right? Well, a dynamotor does the same thing, except it's a motor on one end, and on the other end, it's a generator, or dynamo if you like. And what happens is that thing makes a lot of noise in these older radio receivers, even with the case on. And pretty much everybody that got their hands on these things removed them and put a power supply in the radio itself. And this one here is no exception. This one here has a power supply. So the reason I built an external one is the power supply that's in this radio here doesn't really have the correct voltages, and there's a whole bunch of things amiss with that. So I'm just going to remove that power supply out of here and use this external one. In fact, I think this looks much nicer anyways, and it matches the wrinkle coat of the radio receiver. So that, all with an umbilical cord that runs over to this, should turn out to be very, very nice. Now this will be a very accurate representation of the way this radio receiver worked way back when, because this puts out pretty much the exact voltages that this radio requires, whereas the person that put the power supply in here the first time, the voltages were all a little bit low, so the performance may have been degraded just a little bit. So this is going to be a great video. There's going to be a lot of hints and tips in this video regarding restorations and what needs to be changed in radio receivers like this, or pretty much any communications radio receiver. So join me in this adventure, and I'll share all my restoration knowledge regarding these radio receivers with you. Let's get started. The first thing that I'm going to do is remove the power supply that the previous owner had put in this. So you can see the power supply right here. It's got two big transformers, and it's on a little bit of a chassis. So I can take this out here, and that'll clean up that area, and it'll also give me a couple of transformers for my junk bin again, so I can use them for something else in the future. They look like they're in relatively nice condition. So I'm going to get rid of that, and that's going to leave a large hole here in the chassis. That's where the dynamotor used to sit. What I'm going to do in the future is I'm going to design a product detector for this radio receiver. What a product detector does is basically it just makes sideband much easier to listen to. So I'm going to design a circuit specifically for this radio, and I'm going to also make a universal product detector for many other radio receivers, and I will share that design with you here on this channel. So if you haven't subscribed, now would be a good time to do that, and that way I can cram your head full of knowledge. So I'll share all the design thoughts and everything with you as well as I'm doing that. So it should be a lot of fun. I've got many other communications receivers that I'm going to go through. So for those of you that have been on this channel, you know how many old receivers I have. So it would be nice to make a universal product detector. So what I'm going to do first of all is I'm going to remove this umbilical cord that I added to this thing quite some time ago now, and I'm just going to clip the wires out, and I'll leave just a little bit of the tailings on here, and that way when I go about attaching this cord again, I know exactly where the wires came from, and I really don't even have to think about it. I'm also going to rewire the switch on the front here. This switch originally switched the 24-volt supply to this radio receiver. Kind of odd the way they did this. I don't really agree with this, but you know, they had MVC, right, manual voltage control or manual volume control in some cases, off, and then automatic voltage control or automatic volume control. It can be used as either or. So in this case, this particular radio here, the off is in the center. So what it does is when you're on this side, everything turns on, and it goes off, on. So it kind of gets this off, on jolt every time you want to go from manual to automatic on each side here. So kind of strange, but I would have probably had AVC, MVC, and then off. If I was to design this, it would just make more sense. I don't know why they had off in the center. So they must have had some strange idea for that there, but it just doesn't make sense to, you know, jolt the system all the time as you're going off and on, right? Back and forth, just introducing more issues. So what I'm going to do is I'm going to get rid of this here. So what I'll do is I will desolder. I'll get close to this here so you can see what I am doing. Yeah, AVC and MVC. AVC, again, a lot of the times, depending on the radio manufacturer, it can stand for automatic volume control or it can stand for automatic voltage control. So just depending on who is actually, you know, doing that, what radio receiver or the company that's actually doing that. So that's that wire there. So we know that this one here is going to go to the negative of the power supply. I've trimmed this one off. So we know that this one is the positive of the power supply. It's caught here in the wrapping. And what else have we got here? We got we got the line cord. I don't know if you can see this. Hopefully you can. I'll get you a little closer to this. Right down in here. So I'll just get rid of the line cord. I've got my soldering iron set to blazing hot for this. So these tabs on the older transformers and things like this, they sink off a lot of heat from the soldering iron tip. So, you know, dwell time is definitely a thing. So, and this here looks to be a ground. So I'll get rid of the ground with this screwdriver here. I'm probably gonna have to cut this off anyways, but this is ugly. Somebody's put one of these kind of crimp tabs on here. So it's ugly. I'll replace that later on. And this is the line cord. Oh, that was a line from the transformer. That doesn't really matter because the whole thing's coming out anyways. This is the other portion of the line cord right here. You can see that. There it is, just kind of tacked into place. This block is going to come off as well. There was a factory connector that plugged into this, and with all of these receivers, it's basically missing. Now, I don't want to tie the power supply with the new, this one here has a new umbilical cord right here that's going to run, I'll just back this out so you can see this, new umbilical cord that's going to run to the power supply. So this plugs into the power supply, and then this will be fastened in here to the radio receiver. I don't need this here with these pins open like this, right? Because there's going to be a lot of different voltages apparent on this or present on this, and you know, there's a hole in the back, right? So, you know, I want to keep this as safe as possible. So this will just go missing, and I'll put all of these connections on a terminal tie strip in here, and then this new cable, which will get a covering too to make it look more era specific. I'll put a cover on this. Will run in here and just be tightened down to the chassis. So there's a lot of mods that have to be done to this thing. But in the end, you know what I'm going to do? I'll just cut this. Actually, is this going to slide out at will? So I'll just cut these off because this is going to get cut here. And that comes out. So I have a spare computer cord, it looks like. And these have a higher impedance audio transformer, so they're, you know, designed to drive headsets and things like that, right? So I'll probably end up on that same chassis here that I'm going to put the product detector on in the future. I may even put just a standard audio transformer in here, so this will drive an 8 ohm speaker. I'll leave the factory audio transformer in here so it looks all factory. But, you know, again, this isn't going to be a shelf queen, right? I'm going to use this thing. I want to use this for, you know, for communications. So I like doing AM on 80 meters or 75 meters if you like. I like doing that a lot, and this will probably be one of the radio receivers that I do that with. And I like listening in on sideband as well. Of course, I do sideband as well, but AM is my preferred mode. I like AM. You can also check out my refurbished broadcast transmitter that came out of a radio station. If you look in my videos list, there's another neat video that you may not have seen. I stand inside my broadcast transmitter. That's how big it is. So I'm actually right in the process right now of moving it here. So I've got pieces of that broadcast transmitter actually just outside the frame here. So eventually that case will come here, and I will get back on 80 meters AM again. I know many of you have been asking me about that. You've been saying you'd like to make contacts with me on 80 meters, and I will. In fact, I'll probably make an announcement when I'm going to get on the air. And all of you that want to make contacts with me on 80 meter or just listen in 75 meters, you can do so. So hopefully this is going to do it. Hopefully I got all the wires out of here. Looks like there's 2 screws holding this down. One here and one over in the corner here. Maybe we can lift this big chassis out. That'll leave a nice big hole here in the chassis. And I can put another plate on here and put some... Let's see, will it come out? Have I got everything off? That came out too easy. That was just way too easy. So I got 2 spare transformers now. So I talked about this in a previous video. This is kind of confusing. It's basically 2 power transformers in here. So it really only needs 1 and a vacuum tube and a filter. But yeah, that's what happens. So this here is the area. Look at that big hole in the chassis now. So I can put another solid piece on top of here. I have a bunch of Hammond project boxes that would probably, one of the bottoms would probably be very close to this. And I can just put that on here and that'll fill up this hole, make a nice cap for it, put a tube socket, maybe a transformer on here for the product detector. I think that'll work out real slick. So what I'm going to do now is flip this thing back over again and start removing this thing right here. I'll take you through that process. And after that, we'll start getting into the caps and the components, and I'll start talking about why I need to replace these capacitors. And I've never actually tested one of these fast capacitors on my channel before. So this will be very interesting for both me and you to see if these things are leaky. They're completely sealed, and a neat capacitor, very neat, soldered on the ends and stuff like that, sealed tight. So let's check out and see how bad these things leak, if they even do. So that'll be next. There's a whole bunch of connections on the back side of this block here. So chances are I'm going to have to bridge some wires. They've got connections here, there, and everywhere. You can even see they've got ground tabs. You can see there's wires or capacitors attached actually to this little eyelet here. So there's going to be some modifications to do there. Let's see how this is attached. Does this whole thing come off? I think it probably does. It would need to be pretty sturdy. These things are, look at the size of that, eh? These things are put together very quickly, and of course they need to be serviced in the field. So that is definitely sturdy. 2 big screws that go right through into the chassis and 2 down here. So that would definitely not break. So all of these connections here, you can see there's certain connections that are bridged together, and I'll just zoom on in. Hopefully you can see that okay. So there's somebody's actually added a bridge wire back here. And all of these have to be desoldered and of course put on a terminal tie strip. And looks like these are probably decoupling caps. There's a decoupling cap here, and one here, and another decoupling cap right up here which runs to the fuse. So all of those caps will most likely need to be replaced. They are sealed. Again, we'll test these and see how well they've done over the years. So what I'm going to do now is I'll just desolder these wires back here, and I'm going to most likely have to fit a terminal tie strip in here somewhere and move these from this to a terminal tie strip, which is much further back in the chassis. And I'll use one of these screws, probably with some form of an eyelet, maybe a rubber grommet, to hold the wire that's going to run out of the case here that runs off to the power supply. So I'll get some parts and pieces ready here and move these over. All right, I've got my box of terminal tie strips here, and I was sitting right on top. So I'm thinking I can probably use a screw down here to fit one of these. I don't know if there's enough connections there. Somebody's already used this one. So if you're looking for stuff like this, ham radio swap meets are a great place for stuff like this. Usually this stuff sits on tables, so if you're getting into point-to-point wiring, I think this one might actually be a better choice. Look at all the tabs on that one. That's got 6 tabs with a ground in the center, making 7 total. So yeah, I'm thinking that's going to probably do that, because there's 8 leads on this, right? So I can probably tie most of them off here, and that way, if, say, in the future, it was ever desirable to put this thing back in, which I don't think it ever will be because it's going to have that pre-made power supply for this thing, but it leaves the option of, you know, just removing this and tying them directly to the pin again. I always like to make things very easily reversible. So if, yeah, again, you know, if this was ever to go to somebody down the road and somebody's like, I'd really like to have this connector back in here, I'll hold on to this connector and it will always be in an area where I know where it is. So if I was to ever get rid of this receiver down the road, this would go with it if somebody ever wanted to reattach this. Again, I really don't see the reason with that nice, you know, custom built power supply for this, but you never know, right? So this will most likely go here. So what I'll do is grab another screwdriver that's going to fit in that smaller area. You can see this here. Here's another screw. I'll zoom you in a little bit. Another screw down here. And that's to one of these decoupling or bypass capacitors, if you'd like to call it that. So this goes down in here and it's holding on to something else, so that'll definitely have to go back in. And then I think that would work out really nice right there, wouldn't it? Look at that. Nice terminal tie strip right across here. Well, look at that. It's meant to be. So it'll go right in there, like so. And then the umbilical cord will run here, and I'll put a grommet here and it'll be tightened in and all the wires can go right to here. Isn't that nice? Okay, so now what I need to do is remove all of these wires and attach them to this strip. And I also am going to need to remove this capacitor here, and this will need to get replaced most likely as well. Again, we'll test these here in just a minute and see which ones need to be replaced. They're all over the place in here, so I don't have a whole lot of faith in these things. These have been in this radio since the 40s, right? So get that on there, huh? That should be fun to test. Right, so let's see here. That'll be a good replacement. Probably something like that. So leave those there. Get this out of the way. And I'll show you what I'm doing here. So I'll put a new tab here. Much easier to work with a new tab. So see if this will thread into here. A little tight, it looks like. See if I can get that started. You see that there. So that looks like it should work. Of course, it's going to be difficult, right, and catch under that corner, right? What else is new? Give that a bit of a bend. Put that right there like so. And then this will go back in here, and this gives me a new place to tie the, just like so. Gives you a new place to tie the new bypass cap if it's going to be replaced. So again, we'll end up testing this here in just a moment. I'm imagining that probably most all of these are toast, but so I'll probably vacuum this out too. So that's all prepared. Now that that's there, that's like so. I can put this down here. So yeah, I would imagine I'm going to probably end up desoldering all of these wires first. I might be able to mount that right now so you can see that. It looks pretty good. The previous connector is now completely removed. And the wires have been moved from here to this terminal tie strip right here. So what I've done is I've made a legend here. So if this was ever desired to be put back in down the road by somebody else, you can see they're numbered 1, 2, 3, 4, and then so on the other side. These numbers correlate to that. So the wires that have been soldered in here would attach to those pins. Just to make things easier, whenever I'm done with something like this, I always create a booklet, put that information in there. So if somebody does get this down the road, and again, if it was desired to, put this back in, it could very easily be done. Again, I don't see why you would want to, but you never know. I'll also get rid of all of this stuff here because that just adds to confusion. This was written in here when I got it. These wires here would run normally to the B+. So you can see that this is heat shrunk and there's a piece of wire that runs off of this. So what I'll do is I'll put a standoff here and solder these to here, and that'll get rid of this wire here and clean this up. You can see these wires here are for the filament modification, and so this was done again by the previous owner. And you can see that they've got looks to be a nut in here and a whole bunch of wires that are probably on eyelets or something, squished together in there. So these all go over basically to a connection on the tube socket here. So what I can do is run these to the tube socket and really clean all of this up, get rid of this. Again, I really don't need this big chunk of heat shrink in here. So that'll clean that all up. Now I left a lot of umbilical cord here. So I've got lots of cord because I planned on cutting this quite a bit shorter. And basically it'll be down to here or so, I would say, right? So what I'll do, the reason that I left so much wiring here is because these brown wires in the harness will run up to this switch up here. This switch the power to the radio receiver on and off. So the dynamotor, this would turn the dynamotor on and off, this switch. That is the AVC, MVC, and off switch right here on the front of the radio. So I'd planned on shortening this up. So I need to run the AC lines up to this switch here. So this will be fastened here, and it'll give me a lot of extra that I can run the lines up and make that a nice clean install. The red lead will also go over to this area right here. So it's always a good idea. I didn't know when I was building this how much I would, aside from the AC lines, how much the other leads would run into the chassis, so I just left them all very long. So there is a bit of wire waste, but that, the lengths of wire can be put into my bin and I'll use them for other projects down the road, so really nothing is wasted. Let's test one of these fast branded capacitors and see what condition it's in. This one's rated at 0.01 microfarad at 400 volts. So So this is one of the caps that was on that input connector here. It was one of those bypass caps. So as for physical condition, it's in great condition. So the seal on the end is still soft. So whatever material they've used for that seal is very, very soft still. There's no physical leakage. So chances are what's inside this can has been held tight from atmosphere since the 40s. Looks like there is, some resin splatter on the end. That's common, but other than that, it's, very soft seal there. So what do you think? Do you think this is going to test good, or do you think it's going to test bad electrically? So let's see if it's going to leak electrically. We know it's not physically leaking, but let's see what it's going to do electrically. So I'll attach this to the tester, like so. All right. So now this is on forecast. I'll move this to the paper and poly position. So the tester is off. Right now this is discharge. So obviously this isn't charged up, but this is the discharge and on position. It does two things at the same time. Now when I move this to the upper position, that's going to put this capacitor under test. This scale will start out red and it'll count down through the megohms, and then it'll go up into the gigohms, and then that'll be the yellow scale. And then if it goes through that and this turns green like it is right now, we know that this capacitor is good. If it hangs up anywhere in the scale, we know that chances are this capacitor is bad news. So here we go. And as you can see, it's hanging up in the red scale. So this is 0.01 microfarad. This should have gone zip, zip through the scale, and it should have been green really quickly. So now, if I move this to the forecast position, we can get a good idea if this is degrading inside right now. If it counts towards the bad end of the scale, so if this starts to go backwards, we definitely know that this capacitor is going bad. So here we go. I'll move this to the forecast, which is the center position. Watch the LED here. And look at it, counted towards the bad end. So we definitely know that this capacitor is going away inside. So what I'll do is I'll test a good cap. So this is a modern cap here. Same value, 0.01 microfarad. So I'll put this into the test leads here, just like the other one. Now I'll move this back to the paper and poly position, so it'll give it the same test we did first here. So it's off, this is discharge. Now watch what happens here when I test this capacitor. See how quickly that went green? So that's the difference between a good cap and that other cap. Now, of course, if I move this into the forecast position, that'll just stay green. That's not going to count back up the scale whatsoever. In fact, these caps are so good, it'll actually count down through the whole thing and test it in the forecast position. So I'll just move this to discharge for a second. So that's discharged. Now I'll test it in the forecast position, and you'll see how low the leakage is on this. Look at that. It's actually fully testing this thing in the forecast. So that definitely tells us that these capacitors here are on their way out. We could test another one for a sanity test here just to make sure. So sanity check, make sure that we're definitely testing things okay. What I'll do is I will desolder this capacitor here from this terminal, move this lead out of the way, and I'll be right back and we'll test this one right here. I've got this end of the capacitor desoldered right now, so that runs to this other end of this fast cap. So let's attach the tester and see what we have. So this one's rated 0.25 microfarad at 100 volts, so this will count down a little bit slower. But let's see what happens here. So we'll put that in the paper and poly position, and here we go. That's definitely slowing up. So now, as it transitions, I want to see if it'll count back up. So here we go, if it does transition anymore. There we go, so I'll put it back, yeah, see onto the forecast position, it went back up. So, put it back to test. and then to forecast. As you can see, it's going back up again. So definitely leaking as well. So we can tell that, you know, all of these caps in here are on their way out for sure. So all of them have to go, and there are a lot. So I am going to be desoldering caps for a long time. So I'll just grab something to point with here. I'll zoom on in a little more. So there's a cap here, this cap here, which is easy to see. There's a cap here, a cap here, there's a cap here, one here, there's another one under here, there is one under here. So they're all over the place, as you can see, you know, hiding all over. So all of these caps have got to be removed and replaced. And it's also very important to locate the outside foil portion of the capacitor. So you can see on this capacitor here, we have a lead that's attached to the shell of the cap. So technically, if this is tied to the chassis, this is shielded right up to this point of the capacitor. And then of course the other part that's inside here is completely shielded because of this. So you can almost look at it like almost like coaxial braid right up to the end where the lead comes out. So very well shielded, and that's most likely the reason that they use these particular caps, because this is even better than a wax cap with an outside foil layer, right? So very well shielded, and these capacitors, the replacement ones, that would be, you know, something like this, all of the outside foil on this has to be located so that I can attach that end, if it's a bypass cap, to the chassis, and this end is into circuit. So to give you an idea of how they were thinking when they did this, here's a clear example that the engineers were definitely told to do this. So I'll zoom on into a cap here inside, and hopefully you can see that. Maybe you can. Hopefully you can. Yeah, you can. Get that right here and prop this up. Don't move too much. Okay, so you can see this capacitor right down in here. So this is tied to the chassis. As you can see, it's pressed tight against the chassis. This is ground. And you can see that this runs right up to one of the IF transformers on the top here. And you can see how short this actual lead is right here. That's tying to the IF transformer. Do you see how short that is? And then you'll notice that on the resistor that runs up to this point, we have a very short piece of lead here, but they've left this end really long. So what they've done is in order to reduce lead length, what they've done is they've ran the resistor way down over here, and so they've left this portion long, and then this portion is really short, and this portion into the cap is really short, and it's shielded right at this point. And they've done that for a reason, right? Because they don't want any type of oscillations or interference or anything happening here, so they're keeping the lead length short at a point where it's very, very sensitive. And that's the reason that it's very important to locate the outside foil, because if we technically had this capacitor, see the replacement cap, say that this was the replacement cap, okay? So say we're gonna use this, okay? This one's 0.01, so it's not, but just say we were going to. If we had this backwards, all right, so say that this end here was the outside foil, so this end is attached to the outermost portion of the cap. If we were to tie that to this point, all of that section would be exposed. So from here, all of this would be exposed to this point. And then the internal part that we would be tying to ground would be the wrong end. All right, so this looks like 0.01. So this would be technically the size of the replacement. You can see how much smaller that is. That's quite a ways away too. So when I'm replacing this, I need to locate the outside foil on this capacitor. So the same as the case on this. And what I need to do is mount this really up close to that terminal point there, up to this point here. So very little lead length on this side. We can have longer lead on this side because it's just tied to the chassis, right? But on this side here, it needs to be nice and short. So it'll be like this resistor here. We have long lead on this side and a short lead on this side. Well, there'll be a long lead to the ground point, and then a short, a short portion right here, if it would focus on the capacitor. There it is. So that's what needs to be done with all of these capacitors. Now, some of you might be saying, is it important for all of them? No, it isn't for all of them. It's just important for the ones that are tied to sensitive areas. So as we know, where the capacitors came in over here, right, on that terminal tie block right here, we have lead length running off all over the place here. So locating the foil end isn't so incredibly important on this side, right? Because, either end is going to be long. We have a long wire coming off here going to the power supply, and we have a long wire running off over here. So a little extra lead length isn't so much of a big deal. But when you're dealing with a sensitive area like that IF transformer over here, or any other area where the lead length needs to be short, that is very important to do. And if not, you're going to compromise the performance of your receiver when you're rebuilding it. So it's always a good idea to always locate the outside foil. That's what I do, and I just mark them off and install them at that point. So I'll show you that next. Let's locate the outside foil end of a brand new capacitor. Now, I get this question all the time, and the question is very valid. This is the question. How come they don't mark the outside foil end on these brand new capacitors if it's so important? And the answers are really quite simple. First of all, the majority of these capacitors are now going to be mounted onto a circuit board. They're not going to be mounted in a point-to-point circuit. It costs a lot of money to orientate this thing the correct way and perform another test on an actual production run. On a circuit board, you can have a ground plane layer directly below the capacitor that's acting as shielding. Whereas when you're building something point to point, depending on the builder and how this is installed, I guess you could say there's a lot more variability in the actual build. So really nowadays it would cost the company a lot of money to actually mark the outside foil end, whereas, the customer or whoever is purchasing the component can very easily do that themselves with a device like this. Now, this is something I've designed as well as the capacitor tester here, just to make life a whole lot easier and to make sure that when I'm doing restoration like this, that I'm getting the absolute best results that I can out of the restoration. So I'll show you how this works here. So I'll clip this into the leads like so. So these are the test leads. And I'll just turn the device on. And you'll see the actual display is pulsing. So it's, pulsing there. And you'll see that there's two green LEDs moving back and forth. So the green LED on the bottom here is indicating which one of the test leads is grounded out. So this one is now grounded. This one is now grounded. The opposite lead is the signal lead. So technically what it's doing is it's taking this capacitor and electrically flipping it around, so that we can locate the outside foil end. All right, so now to show you how incredibly important it is to locate the outside foil end, what I'm going to do is I'm just going to grab the outside of the capacitor, and just me standing here, the noise that's surrounding me, and basically, from everything that's around me, is going to be induced into this circuit, and you're going to very quickly see which side is the outside foil. Now you can see both sides are just pulsing right now because it's searching, right? So now the least amount of LEDs that are lit in this row corresponding with the LED that's lit on the bottom tells me which side is the outside foil. So for example, I'll grab the capacitor just like this. Now look at that. Most amount of LEDs there. Least amount of LEDs on this side. That tells me that this side is the outside foil. All right, so you see that? See how incredibly important that is just from me standing here. It's picking this noise up. Right, I move this down here. So this side here is the outside foil. So what I'll do is I'll take this capacitor, just like this. I'll flip it around, and now you'll see that this side here will be the least amount of LEDs lit with the corresponding LED on the bottom. See that? Now this side is the outside foil. Now, you can see how sensitive this is, right? It's very easily telling me which side needs to be attached to the chassis or to the lower impedance portion of the circuit, right? So just think about if this thing was in a chassis with an AC filament lead underneath it and you had put this in backwards. Or just say this is tied to a very sensitive portion of the circuit where there's an oscillator or something like that in the actual circuit. Just think, you could create a parasitic oscillation or do all sorts of crazy things like that if this was not put in the right way. Again, point-to-point wiring is a lot different than mounting something to a circuit board. Now, keep in mind, depending on the sensitivity of the circuit that is actually built on a circuit board, in some cases, this can even matter on a circuit board as well. Right? So there we go. So you can see. So now that I know what side is the outside foil, right, which is this side right now, I'll unhook this and I'll hold this like so, and then what I'll do is I'll grab a marker. Now, not to deface the capacitor, what I do, hopefully you can see this here, is I just put a little dot on the end just like so. A little dot. That now marks the side which would be tied to the chassis or the lower impedance portion of the circuit, and it doesn't deface the capacitor. I'm not scribbling on it or marking any lines or anything on the capacitor itself. Unless, of course, you're looking at the end, you're not going to see that little dot. And you can even use a silver type pen and it kind of blends in with the lead if you're concerned about that. If you're concerned about, anybody seeing the little dot. A lot of the times you can even get a bit of alcohol and say rubbing alcohol and actually remove the dot if you want once this is in circuit, if that matters. But a lot of people actually want to see that so that the actual work has been done, so that you've actually done the outside foil location. So there you go. So both of these testers are devices that I've designed. So this tester and the capacitor tester, these are both available. All the plans, circuit board layouts, alignment procedures, drill maps, everything is all available in my Patreon electronics course. So if you're interested in building one of these things and you feel that this would benefit you in your repairs or your designs, definitely check out my ongoing electronics course. There's a lot more projects like this there as well. I've built many, many customized testers for many different types of, circuitry analysis and all sorts of things. One day I should probably line them all up on this bench here and show everything that I've designed. It would go from end to end. So I've designed lots of custom test gear there. So definitely check it out. And I'm sure you'll greatly enjoy what you find there. Let's take a look at what's hiding under this. This will also allow me to remove this cap. It's fastened right here. So and that is now on the bench. Oh, another cap is hiding under here. They're all over the place. Let's get this out of the way. There's another one here. Another one right down in there. So yeah, they're everywhere. So I needed to remove that anyways, just because, this end of the capacitor here is, underneath that shield. That allows me to move this out of the way. So lots and lots of caps to replace in here. So I'm going to get started on all of these. And once I have all the new ones put into place here, I'll explain what I've done. At this point, it's basically pick a capacitor and start going. So I'll start with this one here. It's relatively easy to see. So the first thing I'm going to do is heat this up and see if it's wrapped around this terminal very well. And of course, if it is, then usually what I'll do is I'll snip the lead short. If it's not, I'll just unwrap it and leave the lead on the cap, just because. So it looks like it may come off okay. So I'll grab a pair of pliers here, put this on here like so. I usually don't like to cut the leads off the cap, just because down the road I may further test them. And I also like to save these capacitor bodies. See, this one here is coming off. Now, a lot of the times, if you're not worried about the cap, you can actually just snip the lead. This one here is wrapped around pretty bad. So usually they're not this bad. There it is. Look at that. How many turns is that? So there's that. I don't like to snip the old cap off and leave the leads on. You know, basically leave the remaining lead on there. It just makes for a very messy situation. As you can see here, it's kind of unwrapped this wire a bit too. I'll clean that up. So now, on this side here, you can see that. I may need to add some solder to this. No, that's coming off. Get that off there. A lot of people, again, as I've mentioned many times before, like to use the J-hook method. So basically what they do is they leave a little bit of lead and just solder to that. And I don't know, I find that that looks messy. A lot of the times you have to add solder to remove solder. And that's what I'm doing right now. Can't actually see which way they wrap this around here. So a lot of the times these things, they sink the heat off pretty well. And as you can see, this one here is no exception to that rule. There it is. So that gets rid of that cap right there, as you can see. Again, the seal looks like it's in very nice condition. Move this down here so you can see that. So one day, you never know, I may very carefully open this and restuff the cap, put a new cap inside. It depends on, you know, who wants the restoration done or something like that, right? So now what I do is I clean the area up. So this wire here is looking a little bit messy due to the removal of that cap. As you can see, this is very time consuming to do a nice clean job. So I'll just vacuum some of the solder off of this. Again, a lot of the times you have to add solder to remove solder. So what I'm doing by adding solder is I'm making a thermal connection between the tip and the actual part. And then by adding the solder, it makes it much, much easier to remove. So it allows you to clean the terminal up very nicely. And down here, I don't know if you can probably see that, I'm probably in the way. There, that leaves a nice clean terminal to resolder a new capacitor to at that point. So I have a whole bunch of capacitors marked at this point, so I've already marked the outside foil. I've done probably about 10 of them. So I have the focus fixed here so that it's not going to be focusing on my hand every moment. So you can see this is the outside foil end, so that would be towards the chassis. Now I can make this quite a bit shorter just because the capacitor isn't so incredibly big anymore, and that is actually a little bit beneficial. So the newer parts are always so much smaller. So I can put that on there like so. And I don't want to wrap this too incredibly tight, so I'll leave a little bit of slack there. You can see there's a bit of an angle on that. So I don't need to wrap this around the terminal post and get real crazy with this. Again, you know, this isn't going to be in a high vibration atmosphere. And that is enough right there to hold that. And with a very nice pair of snips, just snip away the access on that side. And on this side here, pull that up to an area where I can get at that, like so. And re-add solder to this side right here. And then it'll heat the terminal up so you can just feed the solder all over the terminal. And there it is. It's looking pretty good. Nice and clean. One capacitor is in. I don't know how many more to go, so I'll keep on going. I'll tackle this one next and move to this one and move all over the chassis and get these all done. All the capacitors are in on the bottom side here. There was one extra cap that somebody had added, and it's on the cathode of the last IF amplifier. Maybe they added it to give just a touch more gain. So this is 5 microfarad at 150 volts. Let's see how that tests capacitance-wise. So I'll put this on here and here. And it tests 5.3 microfarad. So capacitance-wise, it's still good. Let's see what this tests for leakage. Move this out of the way. This in here. That's not going to glare. So it's on electrolytic here. So I'll put this here and this here, and we'll see what happens. So here we go. And that is leaky. Yeah, that should have been well green by now. So let's put a modern 4.7 microfarad capacitor on there. That would be the modern equivalent to that. So we'll go here and here. Quite a bit of size difference there, right? So here we go. So as you can see, that other capacitor, even though it tests okay for capacitance, it is electrically leaky and it is finished. So you can see where, having a tester like this, just using a standard capacitance tester to test capacitors could be very deceiving. And I see this all the time. All right, let's see what's under here. And more capacitors. Zoom on into that. So it looks like there are 3 caps that will need to be replaced. We have one here, and one right over here. Doesn't look really too friendly to get at, but I'll get these unsoldered and replaced. We're getting pretty close to doing an alignment on this radio receiver. New capacitors installed. Now I can get to installing the umbilical cord on the bottom side of the radio receiver. I'm ready to install the umbilical cord here. So what I've done is I've taken all the leads and soldered them all together with one wire coming off. You're probably saying, what are you doing? Well, I want to put this somewhat of a cable protector sheath over top, and that would look very era specific. So in order to put this on top of this entire thing, I need to pull this wire through because this is going to be relatively tight. So what I'll do is put this through one end like so, and this will poke out the other end, and this will allow me to pull. See, it's already out of the other end. This will allow me to pull this wiring all the way through. So I'll feed this up and over this like so. And you can see how tight that is already. So now when I pull on the wire on the other end, I don't know if you're going to be able to see this. You can see it's moving forward now. So I'll have to edge this through this entire thing and make sure all the wiring is going to cooperate. And at that time, this here should cover this entire wire, and that should look pretty good. The umbilical cord is now installed. It worked out really nice. So the coating matches the era and hides the wires underneath very nicely. So what I've done is I've put this into a rubber clip here. So it's a metal clip with some rubber on it. What I've done is I've put some super glue inside there, and I slid this up inside and then of course, tighten this down to the chassis. And that is one piece now. That is solid. That'll never move. Isn't that nice and clean? Gets rid of that block on the back and just cleans this area right up. So one nice thing about restorations is it usually does a pretty good job of cleaning areas up. I've installed bypass capacitors in here. You'll notice that there are loops here. This is just a strain relief, just in case something was to ever happen and this was to twist or move a little bit. I don't want to put any pressure on the terminal tie strip. I want everything to, remain solid in here. So if anything is to move here, we have a little bit of room, and same with this as well. There's a little bit of room there. That's the reason I bent this out like this. Again, another strain relief. So now what I need to do is I need to take these wires here and run them up here over around to this switch on the front face here. So I'll zoom you in on that. So I will wire tie these up. So I have some period correct wire tying, which I use the same stuff in the power supply, and I'll run this up and over just like this. What I need to do is I need to remove these two wires here and just bridge them together. So just connect them. And then these two will be the terminals that the switch wires go to. So this will switch just like it used to when this thing was flying around in a plane. So AVC will be on, center is off, and then MVC. And it'll switch the power supply, the remote power supply, on and off by doing that. So I'll get these desoldered and these wires tied up and soldered in here, and we're pretty much ready to do an alignment on this thing. The switch wires that run off to the power supply are now loomed, and they run up to the factory switch over here. I removed the two wires that were on the switch, soldered them together, and just put a boot over top of them, an insulating boot, and tucked them behind this harness here. So now this switch here will turn the power supply, the remote power supply, on and off. It should act just the way it did when this thing was flying around. So I did loom the wires, tried to make it look as era specific as possible. Of course, the wiring is more modern, but what do you do? So that turned out okay and gives it that old time kind of look. All right, what do you think? Let's give this a try. I've got everything here. Let's pull this up over here. So, one sec here, I'll just plug this into the power supply here. Bend right in front of the camera there. Okay, so that's plugged into the power supply. You can see all this. Lighting down a little bit. And I do have a speaker off to the side. So this speaker has an impedance matching transformer on it. So again, when I modify this, I'll probably install just a standard 8 ohm output transformer and just let this just basically be in there for looks. Audio transformer wise anyways. Hopefully you can see that. And yeah, I'll turn on the isolation transformer and variax appliance off. Volume's about halfway. Oh, I guess I could attach my antenna here. Let's attach an antenna. See if we get any noise out of the thing. And okay, I think we are ready to go. All right, so it's off. So here we go. Turn on the isolation transformer and variax apply. So here we go. Go to AVC, I guess, first. Look at that. Lights are on. Tubes are lighting up over here. That's a good sign. Just leave everything the way it is. Have my hand on the volume control just in case it gets loud or does something silly. Look at that. Lots of volume. Of course, again, it has an impedance matching transformer. If I was just to tie this directly to an 8 ohm transformer, this would probably be over here. So it sounds like it's trying to receive. It is. Look at that. No alignment or anything. Things working very well. So that is a lot of components that were replaced in here, and for this thing just to come to life like that is a good thing. Probably use a bit of contact cleaner there. See if the crystal works. Oh yeah. It's working. The crystal's even working. Whether it's anywhere near the IF frequency, 915 kilocycles, is yet to be discovered. So it's close though. You know, you could tell as I was moving it around, you could kind of hear that swishing noise, so it's not that far off. There's no alignment. That's right at 5 megahertz. That's the WWV. That's right on 5 megahertz. No alignment or anything. Does the CW oscillator work? It does. So zero beat is definitely off. So that isn't aligned very well, but it's working, which is pretty good. So some things are good, some things aren't. Let's see if the dial lights here dim. Well, they do. Pretty much right at the end, not very gradual, but yeah, they dim. There's a little bit of a howl in there. So all in all, not bad yet, right? You know, the thing isn't even aligned. It has no IF alignment. So if the IF can be peaked up at all, the sensitivity will come up. And if the, antenna and RF sections can be peaked up, and again, we'll gain some more receive there as well. So not bad. Just basically parts removed and replaced, and the thing is really working well. It's spot on, 5 megahertz. That's very, very odd to find that's so incredibly close. Like it's right on the line at 5 megahertz there. Wow. All right, so now let's perform an IF alignment and see how far off this thing actually is and see if we can get more gain out of this. I'm about to perform an alignment on this BC-348Q receiver. Please note, if you're following along, you are doing so at your own risk. Know that all vacuum tube equipment has elevated voltages inside it, and this radio receiver is absolutely no exception to that. This radio receiver, in order to do an alignment, has to be powered up. So it has to be on, and it will have to be moved around. I have to go from the top to the bottom side, and I also have to get around the back side of this radio receiver. So while it is on, I have to be very careful while I'm handling this thing to always be sure I know where my hands are. Again, any vacuum tube equipment has elevated voltages. That's just the way vacuum tubes work, aside from, say, a space charge circuit, which is a little bit different, and I'll talk about those in the future. So again, if you're following along, be very, very careful. You're doing so at your own risk. Let's get started with the IF alignment on this radio receiver. In order to perform an alignment on this radio receiver, or pretty much any radio receiver, 3 pieces of equipment are needed. 2 for sure. The third one, is questionable, but 3 pieces are usually good to have around. Chances are the third piece you have anyways. So the first thing you need is an RF signal generator, not to be confused with a function generator. So you need an RF signal generator that has the ability to go down into the low microvolts. Most function generators will not do that. The second thing you need is a vacuum tube voltmeter or a FET meter, some analog meter that has very high input resistance or input impedance, is very useful to have. And the third thing that you need in a case like this, which is definitely needed, is a digital multimeter that has the ability to read down into the microamp range. And that's for a very important verification step in this IF alignment, and I'll talk more about that. A lot of people confuse this part and they don't align their radio receivers properly, or their alignment doesn't come out very good. So I'm going to share a lot of hints, tips, and tricks with you as I'm going through this alignment. A lot of stuff that just isn't talked about anymore, and actually really isn't talked about even way back when. So this is stuff that servicemen were just required to know, and again, wasn't really talked about a whole lot. So you'll experience all of that throughout this entire alignment. So there's a lot of really good hints and tips here, a lot of, I guess you could say, gold in this alignment procedure. As I do other communications receivers, I will clarify their alignments as well and make them clearer and easier to perform. That's my job here, right? I want to convey this information and pass this information along to you. Now, I'm going to skip most of the steps in the factory manual for this radio receiver. You're probably saying, why am I going to do that? Well, if you were to follow those steps, that's an absolute worst case scenario alignment. So that means that there's something very wrong with the radio receiver, or it's been completely disassembled and put back together and everything is right out of alignment. Chances are, most of the time, if you pick up a radio receiver like this, it has been aligned and it is somewhere within relative alignment, that you don't need that, to follow that manual exactly. Now again, if you were to completely disassemble this, turn every single adjustment in here and put it all back together again, then that might be needed. But I don't think you're going to do that, and I really don't think anybody else has. Just getting these things out of here is an absolute nightmare. So that doesn't need to be, or that chances are that hasn't been done. So you'll be absolutely fine. And again, this alignment is what I'm going to explain to you falls in line with many other receivers as well. So lots of great information to share with you today. So first of all, my RF signal generator is fed through a 0.01 microfarad coupling capacitor into the input grid of the 6SA7 tube, and you can access that grid on the outside of the box right here with this jumper. The input grid is known as grid 3 on the 6SA7, and that's the grid that's in the middle of all the rest of them in the tube, and I'll show you that here on the schematic in just a little bit. Why am I feeding the signal into the grid of this tube and the IF transformer is on the plate side of that? I want to use the 6SA7 as a buffer, so I don't want the IF chain to see my test equipment. In order to get the best alignment that you possibly can, you always want to keep the device under test invisible from your test equipment. So you don't want your test equipment to be seen by this circuit whatsoever, and that's basically what this tube is doing. It's keeping it invisible to the IF chain. It's acting as what would be known as a buffer tube. All right, in this application right now. In a normal application, this is a mixer oscillator, or in old speak, like you will see on the schematic, this is known as the first detector oscillator. Really, this tube's job is a mixer oscillator in modern speak. All right, so that is the VT150, or in this case, the 6SA7 tube. Now, my signal generator is tied to this point, and I also have a termination resistor across the output leads of my signal generator. So right where the leads tie into circuit, I have a 47 ohm termination across that. In order for the output meter on your RF signal generator to read correctly, the output of that signal generator at the end of the cable has to be terminated into the proper impedance, and that's what this is. Now the proper impedance is 57 ohms, or 50 ohms, but this is 47. It's close enough. So we can just leave this here and it'll be absolutely fine. All right. So now This connection between the oscillator and the detector box is very easily found in the BC-348 Q manual, which is everywhere online. This is available everywhere. So this is the Q. You may have the J or any P model or whatever. This one here is the Q, a very common version of this radio receiver, the Wells-Gardner one. So on the box, this is the jumper. This is this jumper that you see right here. I've drawn that in because they don't have the jumper connecting from one box to the other. So the jumper connects from here, goes over, right over here to the detector box. And this is the location and where I'm feeding the signal in. All right, so this is the little part that's on a slant here, the little wall that's on a slant right here. And you can see that it's running up and over to here. I'll zoom into that so you can see. You can see it's running from that terminal down there through this jumper all the way up to the top, and I've clipped to that. Now, I have a blocking cap on the output of my signal generator right here because I want to DC isolate my signal generator from the circuit. It's always a good idea to have a blocking cap of some sort. I have two sticking off of here, but I'm using this one, which is 0.01 at this time. If for some reason the clip lead from your signal generator was to fall off and say bump another wire in here, remember there are elevated voltages because this has B+ on it, and if the output of your signal generator comes in contact with that elevated B+, you'll have a very unhappy signal generator. Unless, of course, it's a vacuum tube signal generator and it has a vacuum tube output, then it just will say, I really don't care. But if you have a solid state signal generator, they're very sensitive. All right. So, signal into this point, 915 kilocycles for this radio receiver. That's the IF frequency for this radio receiver. Most radio receivers are 455, 456, 465, car radios 262, they're all over the place, but most will be 455. This one's a little odd at 915. It's just the way they made this because I think they didn't want any other planes to sniff the front end of this radio receiver. So they moved the IF frequency up kind of out of the standard IF frequency range and gave it a higher IF frequency. They're being a little bit tricky back then. I talk about that in other videos. That's how they used to be able to detect way back when if you had a super heterodyne radio in your house. They could drive down the street with a very sensitive vehicle and they could actually listen to the IF or the oscillator in your actual radio receiver, I should say, not the IF, but the actual oscillator. Remember, anything that's oscillating is technically radiating. So the whole idea to stop that from radiating is put tuned circuits in front of it. So those tuned circuits are tuned to the input, not the actual oscillator frequency. So the tighter you tune the front end to actually what you're trying to receive, the further it'll put the oscillator from the antenna posts so this won't back radiate outside the antenna. Again, what they would listen for is the actual oscillator. So, all right, I'll talk more about that in the future too as I do more communications receivers here for you. So now, looking at the schematic here, again, this is very easily found online everywhere. This here, get this a little closer down here. So you can see the grid that's in the middle of all the rest of them there. That's where the signal is running in, 915 kcs. I'm using this tube as a buffer. Of course, the output, which is the plate here, is running down to this IF transformer, the first IF transformer that we want to keep invisible from our test equipment. What I'm going to be doing is using this microamp meter here to read where the signal is. That's actually explained in the manual itself where to tie this in, and I'll clarify that because all of the manuals, they usually make things difficult. So the line is opened. You see the line that's running through here. The X indicates that the line is opened, and a microamp meter is put in line with the cathodes here down to the actual, it's like a double volume control down here. So I'll show you where it connects into the actual double volume control here in just a moment. It's very easy to access from the bottom side. Now, this is very important to verify the crystal in this radio. You have a crystal filter in here which allows you to narrow things up if you want to listen to, say, sideband, or say there's a lot of signals on either side and you want to get rid of them. Say if there's a lot of adjacent interference, this crystal filter is very beneficial, and it's also very nice for listening to CW in many cases as well. So it gives you a little bit of extra filtering. Now, we need to verify that this crystal filter is still at 915 kcs. Now, chances are the crystal has gotten heavy, and when they get heavy, they go down in frequencies. All right, so the rock is getting bigger. Let's put it that way. So what we're going to need to do is verify this, and if the rock has gotten bigger, we're going to need to make it smaller. And I'll show you how to do that as well. So lots of great stuff in this video here. Lots of stuff that takes a lot of time on my end, that's for sure. All right, so now the VTVM can be put across the voice coil of the speaker, or in this case, even the output windings of the transformer. Do the outputs need to be terminated? As long as you keep the volume in check, you'll be absolutely fine not terminating the output winding, and it'll also give you a little bit of extra output so that your VTVM or FET meter can read just a little bit easier. All right, so this here would need an impedance matching transformer. I have one of those in line so we can listen to the speaker, and I'll explain more about that at the time. There's this big misconception that the output transformer needs to be terminated or some damage to the actual output in the vacuum tube will happen. Not in all cases. If you keep the volume level in check, everything should be fine. Of course, you know, if you can listen to the audio transformer and hear the audio transformer talking, that's probably not a good thing. All right, maybe the volume level is a little too high if the iron is actually yakking away at you. All right, so a great deal of common sense is needed when this is done. And if you follow along with me through these alignments and many more that are coming here, you'll end up being an expert at this in no time. I was going to use a spectrum analyzer to show you the entire circuit, but most people don't have the ability to use a spectrum analyzer. So I'm going to use the most common equipment that's around, and pretty, you know, relatively decently priced equipment as well. So you don't need to be spending massive amounts of money to perform alignments like this kind, right? So signal generators are a dime a dozen. You can find them all over the place, and on the used market, and vacuum tube voltmeters are the same. And DMMs, well, you know about DMMs, right? All right, so I have everything all hooked up here, and I'll show you exactly where I've tied the microamp meter into. So this is where the signal generator is tied into. And I'll just unplug the speaker for a moment so I can turn this thing around, being very careful to note where my fingers are. Okay, so in behind here is a volume control. It's actually two controls. The volume control that's the furthest away from the front, and the terminal that is closest to the bottom. So it's this terminal right here that's closest on the volume control to the bottom. The wire gets removed from that, and a microamp meter gets put in line with that. And that will allow us to determine the actual crystal frequency. All right, so the crystal frequency is going to most likely be different than the IF frequency, because the IF section in these things has probably been screwdrivered 100 times, and a lot of people don't know how to do it properly, and they drag their alignment, as I mentioned earlier. So I'm going to teach you how not to do that. And since the rock is getting heavy inside this thing, chances are the frequency is going to be low. So they all do. It's nothing, you know, it's nothing magic about that. They just, as they age, they go low. All right. So we have growing rocks. That's how it works. Okay. So everything is in line. So what I'm going to do here is turn the gain up. And you can see here we've got quite a bit shown here. And that's because the crystal is out. So what I'm going to do is, first of all, let's do this. Let's determine where the IF actually is at first. So I'll move this over here, and if I plug this back in, I'll get some noise, I'm sure. There it is, because there's no mod. There's the static. Okay, I'll move you over here, and I'll get this all in. So we'll do this first. You can probably turn the output down. So this is the output that's terminated into 47 ohms right here. All right, you can probably turn that down. So I'll turn that down to maybe, let's go 250. We'll start with 250, okay? And then we'll go back over here. And what we're going to do is we're going to look for a peak. on this meter right here, you can see all this, we're going to look for a peak on the meter to determine where the actual IF is. All right, so I'll go one more over here, make this a little quicker. So keep an eye on this. I can disconnect that static right now so you don't have to listen to that. Yes, the output transformer is not terminated. Okay, so here we go. Now you can see we're going up, so we're getting closer towards a peak. So if I go down, see how it's going down? We're getting further from where the IF has been peaked. So we're at 915.5. Look at how far off this is. Wow. How far off is this? Okay, I think we're getting to the end here, are we? So 916,900 would be close enough to say that we're quite a ways off. It's supposed to be at 915, right? Now, another catch here is many times the IF frequency can be tuned if the crystal is a little bit off frequency. So say it's, down 1 kilohertz or something like that. A lot of the times, say it's 916, you could tune it to 915 and things would be absolutely fine. You just do your RF alignment there and you're absolutely fine. If it gets more than a few kilohertz down, say you're like 10 kcs off or something like that, that's pretty bad. That rock is really heavy. So it needs to be trimmed up. So we need to locate where that is right now. So right now, the crystal filter is not in line. So if we look at the actual radio here, you can see the crystal is out. It's pointed to out. So technically on the schematic itself, let's see here, on the schematic itself, right now that switch is closed. It's bridging the crystal. So the signal is not going through that crystal right now, okay? So it's on the out position. Now, we go back here. Again, hopefully it's not going to drift too much. Okay, there we go. So now we know that the IF is roughly 916,900. So we can almost say 917. That's way out. Okay, so that definitely needs to be tuned. So again, this has been screwdrivered throughout time, right? It sounded pretty good when we listened to it. It had pretty good sensitivity, but that's because these receivers they're pretty hot receivers. They work really well, all right? The simpler the receiver, most of the time, the better they hear, believe it or not, contrary to popular belief. Now, what we're going to do is put the crystal in. Okay. So now the crystal is in circuit. So basically that switch is open and it's in. So now look, we're down to 1 microamp right now. So now what we need to do is we need to determine where that crystal is actually sitting to find out if we need to remove the crystal and remove some of its weight. Okay, so I'll move this around here and let's see what happens. So we'll just sweep the area. You can see nothing's really moving because the crystal is very tight. It has a very tight slope to it. So until we get close, we're not going to see an actual difference. So we can go up. And we're even going worse now, right? See how far we're getting from it? So let's go down and see what we get here. Oh, we're starting to climb. Oh, look at this. And we're down. Okay, so now what we can do, we know the rough area. Let's give this just a little bit more RF drive. So I'll bring this back up to say, let's go, let's just try 750. All right, so that'll give us a bit more drive here. All right, 850. Let's do that. That should be fine. Okay, so go back here again. And now that we know that we're relatively close, I'll go 1 digit over to really try and narrow this down. You see we're climbing still. 7.5, 7.6, 7.7. No, we're going back down. So we can comfortably say that this is I'd say the crystal itself is at 912, 990. So that's quite a ways off from 915 kilocycles. All right, so we're pretty close to, say, 913, but that's still quite a ways out. So what we need to do is remove the crystal and bring it closer to 915 before we start the alignment. If we get it to, say, 914.5 or maybe even 915.5, something like that, that wouldn't be too bad. I'll try and get it as close to 915 as possible. And once that's done, once we locate exactly where the crystal is sitting, we want to tune the entire IF chain to the same frequency. So we'll leave it at the crystal's peak and then switch the crystal out, tune the entire IF section, and that way when we tune the dial onto a signal, and if there's any adjacent interference on either side, we'll be right at the peak there, and it'll basically keep all the rest of it out. All the rest of it will be on the slope of the actual crystal. All right. So that's our goal for right now. So technically, before we do the IF alignment on this thing, I'll move you back over here again. What we need to do is remove this crystal down in here. So I'll zoom you in on that. So right down in there is the crystal. This thing right here, it's soldered to the back of the switch. You can see that? Grab something to point with. So you can see they've soldered it to right across the switch lead so you can switch it in and out. And then what they've done is they've taken some leads and they've run them from this board up to this portion of the crystal, and just basically the signal runs through here like this, all right, and this switches it in and out. What I'm going to do, I'll zoom you in a little closer, what I'm going to actually do is I'm going to take these leads and I'm going to solder these directly to this switch. So instead of connecting them at this portion of the crystal, I'm going to connect them over here. The reason that they did this is because the crystal is hanging off the back side of the switch. And if the plane is flying, you're going to have vibration in the plane, and that just steadies the crystal up so it doesn't actually try to modulate this thing, all right, with the vibration. This is going to be sitting on a bench now, and it doesn't need that. And in order to trim this crystal up, I'm going to need to probably put this in and out of circuit a whole bunch of times. So by doing that, I can just tack it in very carefully, and that allows me to not heat up the crystal holder, because if I heat the crystal holder, that's also going to change the frequency of the crystal itself, because when things heat up, capacitance changes because parts expand. So every time I resolder this, I'm technically heating the crystal up, and that's going to cause a drift issue. So in order to give you an example of that right now, what I'll do is I'm going to take a little bit of, I just have some coolant right here. So what I'll do is I'll take some coolant and I'm going to spray the coolant just like this. You'll see this here. See if I can get this in here like so. Maybe I'll have to come over the top side. So I'll spray the coolant on this. See that? I'll just spray coolant on there like so, and we'll take a look at what happens to the crystal. So I have to move the camera so I can get closer to it. And let's take a look. So right now, again, we'll check it again because the radio is actually heating this up. All right, so the radio is actually heating the crystal up right now. So in order to give you an idea of thermal drift, and this is really common, not only in vacuum tube receivers, but most of them. So it's probably even moved from now. Let's see if it has. No, it's actually warmed up. It's pretty stable right here. So we'll leave this at 912, 990. And what I'm going to do is I'm going to spray some coolant on that crystal, and you'll probably see this drop. So let's see here. You'll probably hear it as well. That was spraying the crystal. Now look at that go down. Look at it taking off. So everybody thinks that crystals are incredibly temperature stable, right? Well, surprise, surprise. So you get to see all this weird stuff on my channel, right? Look at that, it's just going and going and going. So once that settles off, I'll move this around. Let's see how far the crystal's actually moved. It's slowing down. Again, this stuff is even valid for modern electronics, you know, not only vacuum tube stuff, right? So that's the reason they have crystal ovens. So let's take a look here. That moved all the way up to 913,160. And that's just because we cooled it off. And that's just because of temperature variation. So that peak is moved. So if we tune the IF to, say, a set frequency and say that crystal gets super hot, it's going to move, right? And that's why it's so incredibly important to let your equipment heat up before you do an alignment. That's why they tell you that in the service manual. So they'll say, let the receiver stabilize over a half an hour, maybe 45 minutes. And it's, again, very, very important. As that heats up, this will move again, and you'll see as it's now warming up again, because there's tubes around it, it's going to change. Now, you'll notice more of a rapid movement in vacuum tube equipment because vacuum tubes obviously are hot, whereas a solid state unit is cold. But the drift is still there, right? It might be from a dead cold receiver to, say, the internal warming of a solid state receiver. There will still be drift there as well. And that's really where the magic in RF design comes in, right? So they did a really good job for the 40s for this kind of stuff, right? But remember, this thing was flying around in a B-17, and chances are it was pretty cold in there when it was flying around, so probably didn't have a whole lot of warming up to do, right? A little bit of trapped heat in the case. Now, when I'm done with the IF alignment on this radio receiver here, after I've shown you this, what I'm going to do for myself is I'm going to put this thing back in the case. I'm going to let it heat up for about an hour or an hour and a half. Then I'm going to slide it out of the case just enough to do an IF alignment and check that crystal frequency again, right? So I'll verify the crystal again. And once that's done, once it's completely warmed up, I'll do an alignment again to the crystal frequency. So this is just to show all of you how this is done. This right now is all in open air, so it's really not getting as hot as it could be. And that's how you get the best alignment that you possibly can. So look at us, we're drifting still. Look at this, how far down we're going. Right, so where are we now? It's probably going down, right? So now we're at 913,090. So there you go. Yes, I notice my meter here is pinned out. Probably turn that down a little bit. Or maybe the lead came off of it. I think the lead popped off. It did. The lead popped off of my meter here. So, by the way, that doesn't hurt these things when that happens. Some of them it does. This one here, it's absolutely fine. So, anyways, so what I'm going to do now is I'm going to get that... Just move this up to another scale, down that a little bit. What I'm going to do is I'm going to remove the crystal from the radio receiver here now, and I'll take that crystal apart and I'll show you exactly how that's done. And let's lighten up the rock a little bit, huh? You know, they've done a really nice job of wrapping that around the actual, look at that. Well, I'm going to have to tackle with that, probably have to get a screwdriver in there and carefully bend that tab out. They've actually bent that through the connection on the switch here. Wow. On this other side here, I don't know if you can see this one here. I'll vacuum this one out as well. So, these don't look like they're too incredibly bad to get off. Get that in there. So again, just moving the little ear off. So that's okay. And then I can just desolder, move that later on. So that's one lead out of the way. And on the other side, it's pretty much the same thing, but I'm going to have to bend that. And that's going to take some fiddling around. Probably have to slide a, let's see if I got a screwdriver here, slide something in here. Like so. I don't know if you can see that. And then probably bend this open. This has got a little bit of a taper on the screwdriver, so it's stopping that from moving. There it is. It's opening a little bit. Yeah, I'm going to be fooling with that for a bit because I don't want to damage the crystal holder. So I'll get this thing out of here and get this on the bench. We'll open this up and take a look at the crystal inside. I've removed the nuts from the screws in the case here, and the case comes apart just like that. And that's the crystal inside. That's the part that's moved in frequency. So this is the part that's so carefully ground to 915 kilocycles. So as you can see, there is some dirt on it. On both sides, actually. So what I'm going to do is clean this with alcohol, and once I do that, I'll handle this with a pair of surface mount tweezers. I don't want to touch this anymore after it's cleaned because I don't want any dirt or debris from my hands on there. And I'll also clean the inside of the crystal holder as well to make sure that everything is nice and clean. And then put this back together and try it out in circuit and see if the frequency has gone up at all. Of course, if it hasn't, I might need to take a little bit of crystal surface off. And if I need to do that, I'll show you how I do that as well. I think I may be able to get away with holding this with these gloves. Because it sure is hard to hold that in a tweezer. Let me tell you. Yeah, you see there is debris on there. Can you see that? So maybe this will help it move up in frequency just a little bit. This is common for older crystals. They need to be cleaned. Again, if they're not, then, you know, they seem to move down in frequency. Let's clean this whole thing off. Sides included. Not just the surface. All right, I'll put that back down. And what I'll do is I'll clean the contacts in here now just exactly the same way. I don't have too much alcohol on there. I'll probably dry that. Yeah, you can see there's some wax in there too. There's that side. And I'll grab this other one over here. And I'll do this side as well. This is the other side. All right, I'll air dry this and drop that little crystal back into the holder and screw it all together, and we'll see where we're at. The crystal is soldered back onto the switch here, and you can see I've bridged the wires from the board directly to the switch now, so this crystal will very easily come out if it needs to be serviced. We left off at 913.090 is where it was working the best before, so that's where we had the most signal. So let's take a look now and see the difference after it's been cleaned. So you can see we're moving up as we move up in frequency. That's a good sign. We've sure moved up a long ways just from a cleaning. And you can see it's getting quicker and quicker. So we're getting closer to the peak. It's moving up faster and faster. So that crystal's really working well right now. In fact, the crystal's working fantastic. Oh, we passed it, I think. Yeah, we did. So it looks like we're settling off at 914,870. So that's about 130 hertz away from our target. That's not bad. So we're allowed to be within 1 kilocycle. And that's well within that. We're only 130 hertz. That's fantastic. In fact, I don't even think I'm going to touch that. So now what we need to do is just tune the IF to that frequency, 914,870. So I'll click the crystal out of circuit now. It seems like we have much more current here as well. I think that, oh yeah. So just the dirt on the crystal was actually hampering its performance as well as causing it to move down in frequency. So that made a really big difference. So this crystal filter section should work very, very well now. Here's that mistake or that catch that gets a lot of repairmen and technicians when they try to search for the crystal's peak using a VTVM across the voice coil or audio output transformer method. It's absolutely fine to use this method for just tuning the IF without a crystal, or searching for a peak to tune the oscillator onto frequency and things like that. Absolutely fine. But when a crystal's involved, you really have to rely on a current meter in the circuit. Here's why. I'll show you. So in order to make this read, because this is across an audio output transformer, I'm going to need to have AC present. In order to have that present, I'm going to need to modulate this. So I'm going to modulate this at 250 cycles. And we'll see a reading on here now. Okay, so we can see that needle come up just about halfway. Now we know that we're at the peak right now, right? 914,870. So if you keep an eye on this here, see it's going down and see it's going down, right? So we're at our peak here. So now what I'm going to do is keep an eye on this meter here, is I'm going to turn the frequency up. You'll see this go down, but this will go up, confusing us, thinking that we're finding the crystal's peak. All right, so here we go. Look at this, we're at 915,060. The current has dropped, but yet across the voice coil, we have more signal. So again, if I turn this back down to the frequency where this is supposed to be at, watch, this will come back up and this will come down. So they're doing the opposite. So what's going on here? So I'll shut this off so you don't need to listen to that. Well, the audio frequency is affecting the reading. If I change this to a different frequency, it will align much closer with this meter. And that all depends on the audio circuitry and how the circuitry inside the radio receiver is tuning with that crystal in there. So it's very important to have this monitoring current to find the actual crystal's frequency and not using the modulated IF and the VTVM across the voice coil method. So don't get trapped by that. So what I'll do here is I'll turn this up to a different frequency. So let's say 1 kilohertz. All right, so we'll go 1, kilohertz. So now this will be modulated at 1 kilohertz. Now you'll see that these will track much more closely now. So if I turn this on, I'll turn on the mod again. All right, the frequency is higher, so we have a little bit less going on here. So now watch this as I go up in frequency now to 915. It's going down like it's supposed to as this is going down. And if we come up to 870, we're at 870 right now. Now when I pass that, it's dropping off again. So now it's pretty much following this. See that? Now these are tracking closer with one another. Again, the modulation is affecting the reading. So other parts of the circuitry inside this radio receiver are tuning. So always keep that in mind. Don't get fooled by that if you're going to try to tune or find the crystal's peak inside your radio receiver. Always use the method where this is in line with the cathode. Very important. Tuning the IF section now is very simple. So I just need to tune these 3 transformers for a peak. So there's a slug on the top and a slug on the bottom. So adjustment here and adjustment on the bottom side. So I'll modulate this signal right now with just an easy to hear signal. That's again at 914,870 where we found the crystal's peak, as you can see over there, right? 914,870. And now what we'll do is we'll peak this up right here. So I'll stick this into here, keep an eye on the meter over there. So we gained a little bit. Now there's an actual slug on the bottom of this. So I'll turn this around. And if we look at that, that's right there. So I'll tune this one up, keep an eye on the meter. So you can see we're tuning this now, tuning it to the actual frequency of the signal generator. All right, and then we'll go to number 2. We can actually just tune the top slugs and then the bottom. It's not really too important in this method here. So I'll go into the second one here. All right, keep an eye on the meter. So we definitely gained some there. I'll go back to the bottom and adjust that one. So that one is located right here. That one's way off. Again, we want to tune the IF to exactly where the crystal is sitting. And that's why we're tuning it right here at 914,870 instead of 915 right on the button. If we didn't have a crystal section, that'd be fine. But since we have a crystal, we want this to work correctly with the crystal. All right, let's go to the third, which is right here. Hopefully you can see that. Move this out of the way of the meter there. That one's pretty close. And again, I'll go to the bottom. And that adjustment is right up in here. If you can see that, right up in there. All right, we'll keep an eye on the meter. And we got a bit more out of that one as well. Or did we? That's close at any rate. So not too bad. We definitely gained some sensitivity with that. So now I'll go back and do these exact steps all over again. You can see we're getting just a little bit more out of it now. So you basically repeat until you have maximum sensitivity. So go back and forth about 2 or 3 times, and everything should be peaked up. Let's just try the bottom one here, and then I will continue the rest of that off camera. Get that out of the way. All right, the hand isn't in the way. Oh, I'm going the wrong way. Yeah, we did get a little bit out of that. So not too bad. A little bit of movement there. So we'll continue on with the rest of them and peak this all up, get that all done, and then we'll go on to an RF alignment. I'm now going to align the beat frequency oscillator. The BFO allows us to listen to CW and sideband with this radio receiver. In order to do that, I need to make sure the modulation on my signal generator is off. So I have no modulation on 914-870. I just have this signal running into the receiver right now. So again, that would be the 400 cycle tone. That's now off. So it's just 914-870. I can turn the volume down, and just like the IF alignment, the crystal can be in the out position. So for the regular IF alignment that was just done, the crystal is in the out position through the entire alignment, and it's the same with the beat frequency oscillator. The only time the crystal is on is, of course, when we're trying to verify the crystal's peak and, of course, testing the crystal and things like that. Once that's done, this can remain off for all the rest of the alignments. So I'm going to turn on the CW oscillator, and I want to tune right now for a 0 beat. So I've got the BFO, or the beat frequency knob, pointed right at 12 o'clock, and that's where I want it to be. All right, so in the end, this is where it's going to need to point to be at the 0 beat. And that's what we're tuning for, is the 0 beat. So I'll turn this on, and you can hear we're definitely not at a 0 beat right now. So I'll remove this knob. I already have this little set screw loose here. So I'll loosen this one off, and I'll take the knob right off. All right, so now I want to twist this until I get to 0 beat, or basically bring the tone down till it stops. Okay, I'll turn this up a little bit. So I'm turning it this way. Turn this up. If you pass it, just go the other way. And that's pretty close right there. Again, this can be moved either side, so we just want the 0 beat to be pointing right at 12 o'clock. So if it moves when you put the knob back on, pull it off and readjust it again. So it's right at 12 o'clock, and it's just slipping on the actual BFO shaft right now, so I could adjust that right like that. Now what I want to do is I want to tighten the knob back on to the beat frequency oscillator shaft at the 12 o'clock position. So tighten the set screw here. That's the easiest one to get at first. And of course you're going to move it as you're doing this, right? And that is pointing directly at 12 o'clock. So once that's done, then you can slip the set screw or the Allen wrench into the other set screw and tighten that one up. This is the easier one to get at. So now when we go either side, we should hear a rise in the tone, all right? So, and that's now aligned. Just that easy. Again, the beat frequency oscillator, the 0 beat is aligned to the IF frequency, so we want it to 0 beat 914-870, and that's what we have right now. That's how easy it is to align the BFO. Very, very simple procedure for that. The next portion of the alignment is the oscillator and the RF alignment right back to the front end of the radio receiver. You can follow this exactly. It is a really pretty straightforward procedure, but there are a few shortcuts that you can take and a few extra little hints I'll pass along on the way to make this receiver work a little bit better at your place. All right, so first of all, the most important things to do are to make sure that you're on the right band before you start aligning anything, or you'll end up having to go over and do your alignment again. So say you forget to switch this and you start adjusting another section, that section that you've just adjusted will need a complete alignment again. So you want to make sure that you're on top of that. You want to use the frequencies that they suggest in order to make the dial track correctly. So this says adjust this at 470 kilocycles. So I'm on the lowest band. This goes from 200 to 500, and I have this sitting right at 470 right now. So if I move this around, it'll go above and below. I want this at 470 right on. So look at the dial straight on and make sure the pointer is right there for the best dial tracking. Of course, if the dial's at 470, your signal generator is going to need to be at 470 as well. They specify 9 microvolts. This will probably be a little higher because this isn't really terminated. It's only going into the front end of the radio receiver. But again, in the end, I'm going to peak this up to my own antenna system. All right, so I'm not really too concerned about that. I want just enough signal in here so that I can peak everything up. All right, it's just that easy. So now 470 is on here. I also want to modulate this so I can see on here and use this as a final peak so I can watch this to get this right on frequency. All right, again, the crystal is out. We don't have the crystal in for any of this alignment. I've got a 400 cycle tone going right now, and as you can hear, there's nothing there. It's just hearing buzzing. That's how sensitive this is right now. It's actually, with my signal generator hooked up, if I touch the antenna post, move this out of the way. So if I turn this down, I don't even want to touch that with the signal generator attached. Look at this. Absolutely right at the end there. So this is already receiving like crazy with just the rest of the alignments that we've already gone through. I can only imagine peaking all the rest of this up, how incredibly sensitive this is going to be. So this will be a really good representation of how well this radio receiver worked. So I'll turn this back up, and as you can see, I'm not hearing anything, right? I should hear a tone. So I'll roll this up the band. Hear that? It's right there. Got to get a good connection on the ground here. All right, there we go. Noisy. So you can hear it just a little bit there. So there's nothing there really. So we're right up at the end of the band. That's supposed to be 470. We're at 500. So what we need to do is put this back to 470. See here, that's about 470 there. Pretty much right on the button. And now we need to adjust. It says here, number 1 trimmers on oscillator, detector, and RF. All right, just that simple. So now, move this around. Make sure that ground is okay. All right, so number 1. So we need to do number 1 on all of these. So you see 1, 1, 1, and 1 is down in here. And that's what we need to do. So let's start with number 1 and bring that right up to 470. Okay. Now all the rest of these are pretty much the same. So I'll show you this one here, and I'll do the rest of them off camera because really it's just, you know, rinse and repeat after this point, right? So I'll grab a tuning tool. That is going to be sufficient for this. This should be okay. So let's move number 1 around and see if we can find it. Whoa! Turn the volume down. So using this. That was really off frequency. All right, that looks like that about there. Turn that down a little bit more. Right, this will also affect this. Are we going to be up at the end of the scale? Yeah, it should be okay. So now we'll go back to number 1 on the detector here. That one is pretty rough. I might have to snap that one open with a little bit rougher screwdriver here first. There we go. Seized up. So let's see. That was pretty close. It was probably that close because it hasn't been actually touched. That was pretty tight. Let's see if this one's going to be the same. Yeah, these are all pretty tight, so I'll loosen this one up here. And maybe we'll go down to this one as well. Let's see that down in there. These ones are usually the ones that gets played with. Yeah, that one's pretty loose. Okay, so let's adjust this one for a peek. That's pretty close, and we'll go to the antenna now. So we got quite a bit more sensitivity out of this. That's not too bad. So we'll just go back up here first and make sure that we're on frequency again. Keeping an eye on this. Hopefully you can see that. Pretty close. Now, if you make a mistake and you say you have aligned this and you poke this into number 2 by accident, you turn that, you're going to have to realign band number 2 all over again. That's one of the catches with doing these. Not too bad. This screwdriver, I might be able to use something that's a little bit more isolated. Let's see if I can use this one here. This might make things a little bit easier. Nah, that's pretty close. We want maximum sensitivity, maximum performance. And that is very close. So now, there's still one extra portion to this alignment here. Just turn this down so we don't have to listen to that. So there's still one extra portion here, the 215 KC patter. So this is really down in where the beacons would be, right? This is a really low frequency band here. They skipped the broadcast band completely in this radio receiver. So there is no broadcast band in this. So the guys that were using this on the plane aren't allowed to listen to the AM broadcast band. So it jumps right over top of it. So now the 215 KC patter here is basically we need to feed that same signal in, but they want us to shut the signal generator off and just tune for maximum static. So that should be kind of interesting. So that's it, and that's this one here on the bottom. So if I move this around, that's this one right here. So I gotta make sure that ground is okay. That's the 215 KC patter. So I'll shut the signal generator off and basically tune for maximum noise. So let's see what happens. We'll see how close that is. If not, I'll turn the signal generator on and see how far off at 215 it is. So I need to tune the front end here to 215. This is not making very good connection in here for some reason. So hopefully that is... So sensitive, this band, right? So incredibly sensitive. Put that in there like so. Maybe that's maybe a little bit better. And that's about as good as that's going to get. All right. Even with this just a little bit of open lead on the bottom here, it's receiving just like absolute crazy. So I'll move you over here to the radio. So 215 they want us at. That's a long ways away. Probably have to put some lubrication in there, right? It's gonna get warm moving it that much. So that's 215. Right there. So that's 215 right on the button. So now we need to tune for maximum noise. So that's the oscillator pattern right here. So I'll turn this back up. That's maximum. So let's see what we get for noise going out of this. Let's see if we can. All right. Now that one's pretty stuck too. Oh. How sensitive that is. Wow. It's going to be a crazy receiver. I have a feeling the reason that they didn't want anybody to actually use a signal generator to tune this is because it's probably so sensitive down here that most signal generators won't go that low. So let's see how close we are to, say, 215. So we'll go frequency 215 kilohertz, and let's turn this on and see what happens. So we'll move over here. Wow, that is really sensitive, but it is off. So I will adjust this with the frequency on. Here with the signal generator on frequency. Okay, so let's take a look at the face. So it is up the band just a little bit. So now what we want to do is we want to go back up to 470 and adjust that, and then come back down here and check this again. All right, so just move this up here. I'll move this back up to 470. Again, this is going to probably need some oil under here or something. All right, there's 470. So let's see if it shifted that. So 470, so we'll go 470 kilohertz. And it isn't there, so yeah, chances are we're gonna have to move back and forth between the two. So go back to 1 again. You can see that down at the bottom here. And on the meter over there. That's pretty good. Okay, so now let's go back. And adjust the oscillator pattern again. So back down to 215 kilohertz. And move this down to 215 again. Okay, so let's see. Go back into the 215 now and adjust that again. So I'll adjust that so it's right at 215. Getting closer. Yeah, it's getting closer. Between 215 and 220, that's not bad. I'm actually pretty happy with that, especially for a band that's going to probably never get listened to. All right, so let's go back up to 470 again and see if we can move that around a little bit as well. So this is how it works with these things. You got to go back and forth on each end in order to either squish or expand the band. All right. It's pretty close now. Not bad. All right. So let's go back down to 215. Again, it's probably going to be close enough. $215 and 215 kilohertz. Not bad. So the peak is going to be between 215 and 220. So probably about 217.5, something like that it looks. Not bad. Still hearable at 215, so not bad whatsoever. That's actually very good. So it's very close to the mark, a little bit above. Now, in order to try to absolutely correct that and make that read on the dial, they didn't even specify to tune for 215 on this, right? They want you to tune for maximum static, basically. So, see, this adjustment uses the noise developed in the receiver as the only signal. All right, so they're just basically telling you, yeah, it'll be around 215 somewhere. Again, this is a beacon band, and that's actually pretty good, so not too bad. So the other bands are pretty much the same. You just go back and forth. I think each band only has one setting on this though. Band 1, band 2. Yeah, so it's basically only 3.3. So there's only one setting on each band. So not too bad. So the only one that has a patter is the lower frequency band. Other than that, all the rest of them are still the same. So for the next band, I would move this up to here, tune the signal generator to 3.3, move this to 3.3, and tune all of them for maximum signal again. Just that easy. So adjust the oscillator and tune for maximum signal. For the fun of it, let's actually see how close this is at 3.3. So once you get up into these bands, this is when it really starts to be a little bit more important. Okay, so there is 3.3 right there. Let's go to 3.3 megahertz and turn this up. And that's a ways off too. So it'll be the same thing with this one. Move this to 3.3. Turn this around. So this is band number 2 now. So this is the one that we would be adjusting. So we want to bring it on frequency first. Let's see that there. So now we just aligned the dial, right? So we're making the dial. Making the dial read correctly. And then the rest of them are just the same. Peak everything up. Maximum signal. Just that simple. Whoa, that one's quite a ways off. Whoa. This band's way out. Whoa. Imagine what kind of sensitivity we're going to get out of this thing now. Wow. Oops, pardon the bump there. Wow, lots and lots of receive on that. So now that's aligned. And all the rest of them are just the same. So I just go and do the rest with all the other bands. And we'll take a listen to this thing, see how well it sounds. I'll get the rest of them done, and we'll take a listen around the bands. The BC-348 is completely aligned, and I have to tell you, the sensitivity came way up on all of the bands. This is one very sensitive receiver right now, and it's working fantastic. So different portions of the bands become active at different times of the day, depending on conditions. So around 7 megahertz right now is active. So let's take a listen into this little area. I'll turn the volume up. I have this on AVC. If we come across any sideband, I'll switch this over to MVC, and that way I can turn the gain up and down right here. I'll show you how that all works. So here we go. Well, there's some sideband action right here. So in order to listen to sideband, you switch it over to MVC just like that, turn the CW oscillator on, turn the beat frequency oscillator either side of the 0 beat, so in this case it would most likely be this side, and turn the volume up, and tune in the signal. There's a conversation right there. It's nice and clear aside from the other noise. So let's turn the crystal filter in and see if it helps out at all.
That just couldn't quite sink in fast enough. Then that'll turn back to ice. So then you get an ice skating rink. But it's a little muddy during the day. I got an early mud season here. It's like I tell people, you know, we don't have 4 seasons, we have 5 because mud season's part of the season. But anyway, we'll just keep it moving along here. I'm enjoying.
So you can see how well that crystal works.
Nice and warm, so I don't have to worry about my battery.
So the sideband sounds really nice. So that sounds like that's coming from a different part of the world. Pretty big sideband signal there.
Yan, Charlie. Charlie pa nakalimutan ko. Charlie, magandang gabi sa dyan. Kaya ni Mang Phil, pero intermittent yata para wala kayong local propagation dyan. Okay, sige, Charlie. Second contact natin ko. Good evening sa dyan. Si NY40X to, si Norman to dito sa Victorville, California. Okay, Mang Phil, balik sa dyan. Medyo malipis sinapasok ni Charlie sa akin dito.
Wow, I heard California in there. I don't know if he's talking out of California or to California. It sounds like he's talking to California. So I'm sure some of you can chime in and probably decode that. So let's go back to AVC here again. Turn the CW oscillator off and everything's out. Sounds like a bunch of frequencies in there, heterodyning. I heard BBC. So that crystal works very well. As I said, this thing's listening to signals from all over the world. And I think that's about the end of the active portion for this band. Let's see. Go up to the top, see what happens. And that's the end of that. Fantastically sensitive, pulls in sideband with ease with just the beat frequency oscillator, no product detector or anything. This receiver really is working well. And again, at this time of the evening, not a whole lot of stuff is happening, and it's still pulling in quite a few stations very, very well. So when this is up against all the other receivers are definitely going to have a bit of a challenge, because this thing really is receiving well. So much sensitivity, you know, that's really loud, you know, right there. I'm very impressed with this radio receiver, and I'm looking forward to actually attaching this to one of my transmitters when I get back, you know, probably on the 75 meter band, and using this as a communications receiver. A lot of fun to use, and it sounds fantastic. If you enjoyed this video, you can let me know by giving me a big thumbs up and hang around. Don't forget to subscribe and tap that bell symbol if you'd like to see more great footage on this channel. If you're interested in taking your electronics knowledge to the next level and learning electronics in a very different and a very effective way, and if you're also interested in gaining access to my inventions, you're definitely going to want to check out my ongoing electronics course on Patreon. I'll put the link just below the video's description under the Show More tab, and I'll pin the link at the top of the comments section. So if you click on the link, it'll take you right there. You can check it out. All right, until next time, take care. Bye for now.